The topic today is the MAC layer. We've already become familiar with parts of the MAC layer. We've seen Ethernet headers, we've seen Ethernet packets, MAC addresses, and so on. So we will discuss this in detail today. To understand how the MAC layer is, and in fact to understand why there is a MAC layer, we need to go a bit through history and realize what the MAC layer was in the 70s. In the 70s of last century, this is how an Ethernet network looked like. And this is how a network at all looked like. You had a number of computers that were connected by a big coax cable, the same type of cable you find in cable TV networks. And then you connected a few computers. I'm showing PCs here. That was rather the 80s. But that technology went 70s and 80s here. And for some reasons, unlike telephone networks that are using switches and centralized boxes, they had the idea of sharing a cable. The motivation was that traffic is bursting. Most of the time, we don't send traffic in computer networks. So if we are not sending traffic, then the cable is idle. So it's a better idea to use the total capacity for everyone. So whatever the reasons, this is how original networks were. They were called Ethernet. We will see that Ethernet can exist in this form today, but very rarely does. And there were things like token ring. It still exists today if you use power line at home to connect your TV to your set-top box your set-top box to your ADSL modem. You will use that kind of thing. And here the cable is not a coax cable, but is your power line communicate the lines that are used for giving power. And of course, it is used today if we go to the wireless domain, Wi-Fi, Bluetooth, Zigbee. We don't have a cable, but we have a wireless channel, which has a lot of similarities. So in this context, what is the problem? Well, the problem is multiple access. MAC stands for medium access control. So the problem is really that if several systems talk together, that can create a collision. Like in this class, if you talk at the same time as me, perhaps we won't hear each other, except if you talk if you don't talk very loudly. There are now different types of solutions. At that time, the solutions that were known were called mutual exclusion. Mutual exclusion means only one device speaks at a time. Like in this class, I'm only one speaking. If somebody wants to ask a question, you raise your hand, I give you the token, and then you speak. That's mutual exclusion. If one speaks, the others don't. Today, we know better solutions that are used in cellular networks that are joint decoding, that allow multiple systems to speak together if the volumes are not too large. For example, if two of you in the back of the room speak in Serbian to each other, perhaps this will not interfere with my French-tainted English, and you will be able to understand both conversations. That's an example of code multiplexing. There's frequency multiplexing, etc. There's a number of tricks that are used to make this possible. Of course, it works as long as the volumes or the powers are not too large. If one system is shouting very loud, the rest will not work. So that is the technology we would use today if we would do sophisticated things. And those sophisticated things are the wireless access links in cellular networks. In computer networks, in Wi-Fi and in old-style Ethernet, we use just mutual exclusion. How can we do mutual exclusion? Well, there's three types of methods. All of them exist in different systems. The simplest one is deterministic. You do a schedule. It has different names. In the CAN bus, it's combined with priorities. Or 2G networks, it was called TDMA. Well, the idea is you have a time structure, so you synchronize all systems, more or less exactly. For example, you have a reference time of 20 milliseconds, and within 20 milliseconds, device A can speak during the first millisecond, device B during the second, etc. So you do a time schedule, which is more or less static. It can be static or be updated on the fly, and that avoids collisions at all. But it works for relatively small systems like buses or old systems because it requires synchronization and is not very efficient. Another mode of operation is token passing. The token passing is used in old style, and not old style, in a specific set of systems that are not so popular today, but exist in application layers that have the same problem. That's what I mentioned when I say in the room, someone speaks, you can speak only if you hold the microphone. If you have the microphone, you speak. When you finish speaking, someone else has raised their hand, so you have a protocol for moving the microphone or the token around, and every host takes turn and passes a token to the next one. Compared to that, it's deterministic in the sense you know when you have the token and you know that no one else, you're not taking chances. But it's more flexible here. If somebody needs to speak a lot, like me now in this room, I have the token much more often than other systems. So it's more flexible and easier to use than deterministic systems. And there's a radically different set of mechanisms which are based on random access. Randomization is a mechanism for solving distributed problems that are hard if you're willing to pay some performance penalty. And this is exactly what we will see in the coming slides. This is what Wi-Fi, old-style Ethernet, power line communications, and many systems are based on. So let's say a few words about random access methods. The simplest of all that exists in various forms today, for example, in the signaling channel, when you connect to a base station of a cellular operator, you use a protocol of this type to establish communication. Sometimes Wi-Fi, when conditions are bad, is functionally equivalent to this. So the simplest of all protocol is called Aloha. Aloha stands from, it means hello in one of the languages of the Hawaiian Islands. So imagine here, you're in the 70s and you have computers that want to talk to each other, and those computers are in different islands, physical islands in the middle of the ocean. You have, at those times, did not have peer-to-peer communication, but you had big computers that were big physically in the space, in the footage that they were occupying, but they were very small compared to the power that we have in today's computers. So you had a computer in the main island, and in remote islands, you had other computers, and you wanted to do communication over radio channels. So it was the very first radio network for computers here. Now, since the system was centralized, there is one direction where there's no problem from the center to the different remote. And also we're using here a single frequency for the downlink from center to the remote and the uplink from the remotes to the center. Now, from the center to the remote, there is no mutual exclusion problem because there's only one system that speaks. So that system knows when it is speaking to whom, so it can take turns, have whatever scheduling method to decide whom it is sending things to. So there's no collision problem, but there's a collision problem in the reverse direction. If a remote speaks to the center, there might be another remote that speaks at the same time. And the idea of a randomized access protocol is to some extent, to allow this to happen and have things that hopefully will work. And if it doesn't work, fix it and hope that in average, it is still better. The Aloha principle is the simplest of all. It means simply that whenever a remote has something to send, it simply sends a packet of data and waits for an acknowledgement of this packet to be sent by the center. So this acknowledgement, we've seen this when we spoke of the stop-and-go protocol. It is a variant of the stop-and-go protocol where we have multiple sources here. The acknowledgement serves the purpose of detecting whether there were error in the transmission, but also to detect collisions. If someone else was sending at the same time, there will be a collision in the center that will receive a superposition of two signals. If they are about of the same power, it will not be able to decode. There will be a collision. One signal is creating noise to the other and vice versa. And therefore, the center will not receive anything and will not act. So here we will time out. And after some timeout, we detect that there is a loss. We need to be a bit smarter, and this is what the algorithm does. So we send a frame, we wait for an acknowledgement on the return channel until a timeout. That's the stop-and-go protocol we have seen already before. If we receive an ACK, then end of the story for the remote. It can go to sleep again. It has done its job. Otherwise, you will try again. But of course, if you try again and the absence of ACK was due to a collision, because someone else is sending, if the two guys that are sending retry immediately, then that might cause synchronization of the two and an error again. So the collisions will repeat themselves almost deterministically. So we add here a random time. That's what we'll discuss in some details a bit later. So we wait for a random time, and with chances, when one of the two tries again, the random time chosen by the other is different enough such that there is no collision. That's the principle. Of course, the performance of this is not very large. The maximum utilization with random numbers, with random emissions, if there is no synchronization, time synchronization of the sources, then the maximum utilization is 18% of the channel. That means if the packet arrivals are purely random, Poisson processes, then we can, with reasonable, the throughput that we can sustain over the long run is only 18% of the throughput of the channel, which is very small. So it's not the best method, of course, but it's one that still works here if nothing else works. So as I said, it's used, for example, to bootstrap communication when today in more modern channels. At that time, it was improved a bit by synchronizing all the systems. So we time synchronize at some granularity the different hosts, and we obtain what is called slotted ALOA, which means that when I send a packet, I can send it only at the beginning of a slot. So that's similar to the parking lot. If you have a parking lot with slots, then you can pack more cars than if it's a completely random area where cars can park anywhere. Then you will have unused spaces that are more difficult to organize. Then if we use slotted ALOA, we can double this utilization factor, but that remains not very good. That was the starting point of the engineers who developed the original Ethernet. So they used this idea, but they improved it because the systems are on a cable, and on a cable transmission is much better. In particular, we can do one thing, which is called carrier sensing. The idea here is that whenever we send a packet here, so we do the same, but before sending a packet, we'll listen whether anyone is sending. So like you do in this room, if you're polite in a room before speaking, if someone else is speaking, you refrain from speaking. So that's exactly what we do. So that's carrier sensing. And you add this. Other than that is the same, and that dramatically improves the performance. Does it totally prevent collisions? What do you think? Question on speak up. I close the poll in a few seconds. There we are. The majority says C, which is true. Let's see why. Well, let's do the usual thing we've done several times, a time and space diagram. Here is an example where A sends on this bus here, and A senses that nothing is happening, so it sends a packet. But by the time the packet reaches B, well, B also had done the same thing and sensed that nothing was happening. But as we know, the propagation time is non-zero, and at the speeds of the electronics where those things are happening, this is not just a detail, it can really happen. And there can be a collision. So here you see there's a collision in this part of the medium. So if you're analyzing the cable here, you have the two signals that are superposed here, and that might not work here. So collisions are possible, and therefore this system improves on ALOA, but is not perhaps the best that can be done. On a cable system, the best is achieved by adding what is called collision detection, where we add here. So we do the same as we said before. We send we wait until the channel becomes free, then we send a frame, and then we do not wait until we receive an ACK, but instead we monitor the channel while sending and seeing whether there is a collision. If there is a collision and we stop transmitting, we wait a random time and we send again. Otherwise, we believe it's okay. So the acknowledgement is replaced by the collision detection mechanism. Of course, this does not always work. So this is making a strong assumption, which is true on many cable systems. It is the assumption that any system can hear any other system. So if there is a collision, the source can hear it. So let's see an example here. A sends to B. A senses that the channel is idle and therefore starts sending. At about the same time, B does the same thing and B starts transmitting, but now B senses that the channel is not idle, so it sees that there's a collision. B sees the collision here, so B will stop sending. In fact, if you look in detail at the algorithm, we see we transmit jam bits. So the jam bit simply means to make sure the hardware reliably detects the collision, we send it for a long enough period. So if you send for a short period, it might not be reliably detected. So, but we're not sending any data here. It's collision anyhow. Everything we do is lost here. So it's just making sure the collision lasts long enough. It lasts long enough for A to detect it, because now A that is also sending will detect the collision. So now A and B have both detected the collision. Here I'm making the assumption that the signal received at A from B is strong enough for A to be able to see that B is transmitting, which means that the cable is not too long or there is no obstacle in between in the quality of the cable. And then the protocol says both compute a random time, which of course is chosen to be multiple of a quantity that is larger than the round-trip propagation time plus the transmission time of a minimum frame. And that, so for example, A has chosen T1, B has chosen T2. Now, both remain silent until they time out. Now, at this time, B tries again. There is no collision. It will transmit. A will time out at time T1, but of course, A will not transmit at time T1. It will wait until there is a termination of the packet sent by B. This is how the original Ethernet was defined. And there are small side effects. We assume that the channel is not, the network is not too large, or the powers are strong enough such that when B sends, A, no matter how far it is able to see that B is sending here. That's what we call the transitivity of the medium. We assume that everybody can see everyone. But here, there might still be a small problem. For example, here, if the propagation time is large compared to the transmission time, we might be in a situation like this. What is happening here? Here, collisions is detected only at those parts of the diagram where there is overlap of the two colors, which means here that when A sends its signals, the signal of B is still propagating on the wave, so it's not present at A. And when A receives it, it's after. So from A's viewpoint, there is no collision here. But of course, there is collision for C. And since we don't know who the intended receiver is in this MAC protocol, access protocol, then C might have a collision. So there might be a collision that is not visible by some devices if the propagation time is too large, the round-trip propagation time is large compared to the transmission time. This will not occur if the transmission is long enough. So how is this solved in Ethernet? Well, in Ethernet, we are really in a region where the propagation time is large. In particular, the faster we go, at 10 or 100 megabits per second, we need to do something. So the thing that is done is to impose a minimum frame size. So an Ethernet packet must always be at least 64 bytes, which today is very small. I mean, given the size of the IP header, 40 bytes, the TCP header, 20 bytes, the Ethernet header itself, 10 bytes. So in practice, it's no big deal. But when this was done, and for some applications that are using compressed header, this might need to be taken into account. So there's a minimum packet size so that the transmission time is large enough, and also a maximum cable length such that the propagation time is not too large. So at those speeds, which are the historical speeds, those are the values. Today, most Ethernet is at 1 gigabit per second, and then this is multiplied by a factor 8 here. So this is the historical Ethernet. AppleTalk was the same. You share a cable, and this cable could be physically shared by having fancy connectors, T connectors, or even you could, if you do it at home on a small size network, if the cable are not too long, there's a loss of quality of the signal if you do it manually, but that was possible here. This is called half duplex Ethernet. Duplex means what? Duplex means that the communication on a cable works in both directions. And half duplex means it can work in both directions, but not at the same time, which is exactly what happens on such a cable. It can happen in both directions of the cable, but there is this medium access protocol that prevents two systems to speak at the same time. So for example, if A talks to B, then the medium access will make sure that, as we have seen in the previous diagram, B speaks first, for example, and then only A. So it's half duplex. Wi-Fi is very similar. Wi-Fi is perhaps the most frequent use of those ideas, with zillions of optimizations. So the Wi-Fi standard is about 3,000 pages. So we'll not go through it. It's also not the main focus of this course. But essentially, it's the same idea. It is not called CSMA-CD, it's called CSMA-CA. It uses acknowledgements rather than carrier sensing to detect the collision. It still does carrier sensing, so it's carrier sensing CSMA. So when a device wants to send on a given channel, Wi-Fi has multiple frequency bands, and you use one channel inside the frequency band, then the system will listen whether something is being transmitted before transmitting. So this is the CSMA part. But the CD part doesn't work. It doesn't work because of the so-called hidden terminal problem. If C is sending to the base station B, we cannot guarantee that A sees that C is sending, depending on the configuration of the room, depending on the powers. So the power sent by C might be just enough for B to receive, and for A, it's not visible. It's just ambient thermal noise. So A doesn't know that C is transmitting. So the Wi-Fi channel is not transitive, which makes its performance less good than that of CSMA-CD on cable systems. And the zillions of optimizations that I've mentioned are trying to mitigate this problem. So one of the mitigations is to use RTS-CTS, which may or may not be used. There is a dispute on whether this is useful or not. It's useful in many settings, but not all. The RTS-CTS is the idea that you send a very short message first, that when A sends to B, for example, and this message is acknowledged, that's the CTS, but it's acknowledged to everyone, and like it must be done on every shared medium access, which will amplify the range of A. In particular, if the problem was that C could not hear what A is saying, this problem will go away. C will see that something is going to happen, and the CTS contains a prediction of all the times it will take to do the data transfer and the acknowledgement here. So C knows it has to defer from some time here. So this is one of the main optimizations that has been done. There's a zillion number of other optimizations. For example, a more conservative random backoff. In fact, when A senses that the channel is idle, it will wait for a random time before immediately transmitting, which decreases the throughput seen from A's viewpoint, but will, in some cases, mitigate some of the collisions. Also, I mentioned that in the RTS and CTS exchange, there is some information that can be used by C to infer how long the channel is going to be busy by this set of events here. This can be used also in the data packets themselves. So when you send a frame, you expect an acknowledgement to be sent. So if you don't use RTS, CTS, you can send in the header what is the length of the frame and the length of the expected acknowledgement, so that anybody who overhears just the beginning can know how long it will take. So that's something which is called sometimes logical sensing. plus a number of other optimizations, but essentially it's very similar to CSMAC. It's very similar, and in particular, what does it mean if I have a Wi-Fi network with a single channel, so a single frequency band and a single channel inside this frequency band? And my Wi-Fi network is made of a base station and a number of hosts that speak to it, like us in this room here. How many frames can be transmitted concurrently? Is there any form of parallelism possible for this system? I close the poll in a second. The majority says A, and it's the correct answer. We would love that one of the other answers is possible. And this is true if we have more sophisticated systems like the cellular telephony, 4G, 5G systems that have different codes or frequency channels for the uplink and the downlink. But here it's not the case. So that means at most one frame is sent in total. So when A sends a frame to C, first the frame must be sent to B. Then it must be repeated by B to C. And while this is happening, the channel cannot be used for anything else. This is why the performance of Wi-Fi is not as good as the nominal performance. If I have a Wi-Fi link at 50 megabit per second, I will never have a useful throughput of 50 megabit per second. So that's the Wi-Fi and old-style historical Ethernet story. Today, Ethernet is not at all using any of that stuff. Ethernet underwent a major change through the invention of what is called a switch. Well, no big invention as it seems from today, but that was a major change. A switch is, from a hardware viewpoint, the same as a router, except it looks at MAC addresses and MAC packets. And this is why sometimes I say, given the way this Ethernet is, we don't really need switches. So probably if it would be done today, people would realize that instead of connecting all my systems through a big coax or other type of cable, I connect them to a router, and then I route the packets immediately. This is what I could do. In the 80s, when this was invented, this is not what was done. Remember that in the 80s, IP was just an obscure little thing done by a few universities for their own fun, right? The real world was not using IP and was not using TCP-IP. The real world was using Microsoft, IBM, DECnet, and that type of, and Apple's networking systems. So a router was a very complicated thing because you had to understand all those protocols. Many of them were proprietaries, they were changing all the time. It was, if you would do a box like this, it has to be a multi-protocol router. It's very complicated. So instead, what people did is a switch. So what is a switch? Well, a switch is like any router, a queuing system. The very first, today's switches are hardware specially developed for that. The very first switches were PCs, computers, that had a processor and a number of Ethernet cards. And what they would do is they would receive on their Ethernet ports all the packets that they hear. And then they analyze the MAC destination address, and then they send it to whoever needs it. Right? Same as a router does, right? Except we look at the MAC addresses here. What is the major difference here is now the cable between a host and a switch can be what is called full duplex, because there is no medium access. We just have a cable between A and the switch. So there is no collision. The only collision that you could have is if you're a bit stupid and you use the same cable to communicate in both directions. But of course, immediately the engineers who developed that doubled the cable so that it allows communication in both directions. And since now the communication is much easier, there's no collision, so noise levels can be higher. They used also much simpler cables than telephone wires were used. So we see here two pairs of wires, one for one direction, one for the other directions. So this is what the evolution gave here. But because Ethernet existed in the old style before this, people added a requirement, which is very typical of anything we do when we evolve a system: transparency. The bridges have to be transparent in the sense that when three hosts are connected to each other through a cable here, they should see no difference whether they are connected to a cable or to a cable that's in a box, which were how the very first Ethernets were. Very quickly, people realized that having a cable that goes from office to office and winding around is not a very good idea, because it's a nightmare to debug it. If the cable is broken or has a defect somewhere, you need to have oscilloscopes and analog analyzers to find where the problem is. So what people did instead was to put the Ethernet in a box, and then everybody's connected by a little access cable to the shared medium, which is in the box here. That's called a physical layer concentration. You can think of it as cabling. It's just a cabling box. It can be also electronic, but mentally speaking, it's the same as before. If we replace this by a switch, then the requirement was that from the host viewpoint, it should be the same. You don't see the difference, which forbids the bridge to be an IP router, for example. You cannot analyze IP headers because really, if you're connected directly or not, you will see the difference here. Bridges must know where to send packets. So for that, they use a forwarding table. For example, this bridge that has three hosts connected to it has a table that maps every MAC address to an interface number. So it has here, A is in port 1, B is in port 2, etc. So the bridge, if you write a program to do the bridge work, then it will listen to all traffic on all interfaces. For every received packet, read the destination MAC address, go to the table, do an exact match into the table to find the destination interface, and send to this here. Now you still need to handle the error cases. As usual, that's the most difficult part in any program. What do you do if the destination address is not in the table? Well, it is not in the table. It could be because there's an error. So this is what an IP router would do. If the IP router goes to its routing table and sees, I don't know what to do with this packet, there is no decision that I can find from my routing table, then I will drop the packet. And if I am a router that is allowing this, I will send an error message, ICMP error message, back to the source. This is destination unreachable. Bridges don't do that. In contrast, and we will see why in a second, if the destination address is not in the table, you broadcast it to all interfaces. So if B sends a packet to A, and for some reason the bridge doesn't know where A is, then the bridge will send it to A and to 3. Of course, you don't broadcast it back to the interface where it is coming from. So that's the program and how the very first bridges were done. Why do we do it in this way? Well, because that supports the automatic learning. So do we need to configure a bridge? No, because a bridge should be transparent. Again, whether I go to Migros to buy what is called today an Ethernet concentrator or a multi-port Ethernet, an Ethernet port amplifier, right? When you buy this box here, it's just like when you buy an extension cord with multiple sockets for your power cables. So it should work without new configuring. So most people don't even know that there's intelligence in a bridge here. So that should be completely plug and play. The way it can be made plug and play is by learning. We've seen that if the destination address is not in the table, it will still work, not efficiently, but it will work in that the packet, called frame because it's an Ethernet packet, is broadcast to all interfaces. And the packets contain a source MAC address. So this is how bridges work. They look at all the source MAC addresses. So if B sends a packet to A, and for some reason A is not in the table, for example, because you just bought this bridge, and so nobody is in the table, then the bridge will send it to all interfaces, so A will receive it. If you have a protocol where B sends to A, and A never replies, then you're stuck. The bridge will never learn, and all packets to A will always be broadcast. But those protocols are extremely rare. There's quasi-none that does this. So most protocols always have an acknowledgement. For example, if you're using TCP, then A will reply. Even if A has nothing to say to B, A will send acknowledgement. So A will somehow reply, and then the bridge will see, oh, now I have a packet with source address A on interface 1, and I write this here. So this is how bridges learn. They learn promiscuously. They just watch everything that happens, and they learn where things are. This is how they can be plug and play. Now, I've shown only one bridge. If you want to extend your cables at home, you can do things like this. You can have coming, for example, A is your ADSL modem connection. You connect to devices here, then you pull an Ethernet cable to go to another floor or another room of your apartment. Then you can put another bridge, etc. Or at least we hope that this will work. Do you think that this will work? I close in a few seconds. Closing. So the vast majority says A, but you're a bit too optimistic. It's true that you can buy your 3 bridges from Migros and connect them in this way and it will work, but not the way I said. There is a problem in what I said. It will work in the topology that I've shown here, but it will not work if there are cycles in the topologies, if there are loops. So perhaps at home, if your goal is to extend from floor 1 to floor 2, you will not create loops. But in an enterprise network, you probably want to create loops because loops are the simplest way of having some redundancy. If there is a cable that breaks or a bridge that is breaking somewhere, having a loop provides some redundancy. Now, if I've created a network that has this redundancy, then there's a problem. For example, B3, when it receives a packet from A, cannot know whether this packet will be coming this way or that way, because if nothing is known, it will be broadcast. So first we'll have a problem. The broadcasts will, as we have seen when we spoke about TTL, they will go along the loop. So they will create a performance problem. They will congest the network by turning forever. Even if we have a mechanism that, like TTL, for preventing them from turning, we're not sure because each of the bridges are queuing systems. So the time it takes to cross a bridge is a non-deterministic quantity. It depends on when other sources were sending packets to the same destination. So you're not sure whether the shortest path from A in time from A to E is this one or that one. And in fact, that might change over time. So B3 might think that A is on port 1 or on port 3, and that might change all the time. Yes. So flooding doesn't work, and even knowing on which path the thing is doesn't work here. So how can we fix that? We have the same problem in routers, but in routers we don't flood. So we have, as we will see, routing protocols. In bridges, we fix the problem in the simplest of all ways by preventing loops from happening. So you can create a network of bridges with any arbitrary topologies, but we will put software into the bridges. In fact, we require that bridges run some software to prevent loops from happening. And this is called the spanning tree protocol. So all bridges, if you're a bridge, you must run the spanning tree protocol that will have the effect, for example, on this network to disable 3 of the ports to prevent all loops from happening. How does the spanning tree protocol work? That is very simple. It was invented by Radia Perlman, who also wrote a poem to explain its working. So as it says, first a tree is built, And this tree must span every LAN. So that's old technology. LAN at the original, when Radio Perlman did it, the bridges were not used, as I said, to replace the shared medium Ethernet, but to interconnect shared medium Ethernet. Then very quickly, people realized, well, if we are able to interconnect shared medium Ethernet, we can do one shared medium Ethernet per port. And if we put two cables, it's not even shared medium. So that didn't last very long. But that was the original idea. So here we should say packets can reach every port here. First, the root. So you create a spanning tree. How do you create a spanning tree? First, the root must be selected. That means all the bridges speak to each other by sending a packet to all their neighbors, saying, here I am, here is my ID. What is the ID? Well, you take one of the MAC addresses and you can configure, or by hardware, it comes with a configured ID. And then it's a gossiping protocol. So all bridges know the IDs of all their neighbors, and they select the best one, and they pass along the information. So very quickly, by speaking to the neighbors, they know who has the smallest number, who has the highest priority of all bridges. And this guy is said to be the root. It's the head of the spanning tree. And then least cost path from root are traced. Well, there is an algorithm called the Bellman-Ford algorithm. We'll see a variant of that called Dijkstra's algorithm for computing shortest path. So all the bridges can speak to each other to find their destination to the root here, and then they follow the direction to the root. This is similar to what we call distance vector routing that we will see in 2 or 3 weeks. And once this is done, we have created a tree, and all the links that are not on the tree are removed. So I encourage you to look at this poem, and I put it in music here if you're interested. So that's all the details are explained. Of course, you want it to be plug and play, which means that you want it to resist to any change in the network. In particular, if you have loops, that's probably because you want to resist to be resilient to any failure. So the topology might change because a bridge goes down. All the systems that are connected to the bridge will lose connectivity, but you would like that at least the rest of the network doesn't lose connectivity, or a cable is cut somewhere. Then if a cable is cut, if there's a loop, you should be able to go around the failure. So the third element is that all bridges monitor that the root is reachable by sending a beacon. So once in a while, they ping the root, and the root replies on the spanning tree. And if bridges, after a number of seconds, have not received the reply from the number of replies from the root, they declare that the root is dead, and they restart the procedure, which might lead to the election of a new root if the network is still fully connected, and a new spanning tree that will go around the failure because the link that is failed doesn't exist anymore. If the network is partitioned into 2 or more connected components, then there will be one root per connected component. So it's completely plug and play. The software is the same in all bridges. So that's an example of what is sometimes people say a bio-inspired algorithm. It's an algorithm where every bridge has the same code, but plays a role that depends on what happens, where it is in the network, and the history of the net system here. So for example, if so in order to run, this algorithm will compute shortest path, which you can configure, but in practice are configured by default because you don't want to have to do configuration. For example, if you have links that are at 10 gigabit per second, you will give them higher priority, smaller cost, than links that are at 100 megabit per second. So assume here that's the case. You have a network where some links at 10 gigabit per second and some links at 100 megabit per second. So automatically the bridge give them a cost corresponding to their physical quantities. And if I deploy a network in this form, it's a bit weird. Why do I do it this way? But okay, let's assume we do this. What will happen? What will be the result of this algorithm happening everywhere in all the bridges? I close in a few seconds. Closing. The majority says B, which now is the correct answer. So the root is B1 if we believe that B are truly the IDs. So the smallest label is B1. So B1 will say to B2 and B5, I am B1. Now B5 has also received from B4 the ID B4. So B5 elects B1 and passes the information to B4, and etc. So at the end, all hosts, all bridges know that there is a bridge called B1, who must be therefore the root. And then they start this Bellman-Ford algorithm that we'll discuss a bit more when we say a few words about distance vector routing, that consists in computing the shortest path from self to B1. So B6 has no choice. It can go only to B3, but B3 has several choices. It can go to B1, directly via to B1 or via B2. But the direct path here has a smaller cost, so that's the shortest path to B1. Similarly, B2 has a number of alternatives too. It will choose B1 because here there's a larger cost, etc. B4 also will decide that in order to go to B1, this is here. So there is no global map of the network. And what we're showing here is an emerging property of the computations done by every bridge, but no bridge knows this complete figure. B4, for example, only knows that it has two neighbors, B5 and B3, that there is a root called B1, and that the distance to the root is 101, and then the next hop towards the root is B3. That's the only information that B4 has. But this information is sufficient. B4 in particular knows that I have a link that goes to B5, and it's not the shortest path to the root, so I disable it. So this link is disabled, which means that B4 will do as if this link did not exist, and same from B2 to B3. Now, B1 will beacon packets that are broadcast on the spanning tree. So B4 will, every few seconds, will receive a beacon from B1. And if this beacon is not received n times consecutive, if n consecutive beacons are not received, then, for example, B4 will restart this procedure. That might be because B1 is dead, or because the link here, B1, B3 is dead. If that happens, then B1 will still be re-elected, but another path would be computed via B2, for example, and another spanning tree would be computed. Voila, this is what all the little boxes that are called Ethernet box or multi-port boxes, this is what they do to prevent loops from happening. We do a break and we resume at 1:15. We have seen that the spanning tree protocol must run in bridges if there are potential loop topologies, and it works in most bridges. So in the lab, in the software bridges that you will use in the lab, you may have it, or you may disable it because it's in software. But when you buy a product, a hardware product, in principle, it's enabled. What is the side effect? Assume I have a ring of 4 bridges wired in this way. Then somehow, we don't know which one, in particular, if you buy 4 elements on which you don't have any control, one of the 4, depending on its ID, which may be just a random number, will be the root. And it means that one of the links will be disabled here. In particular, the traffic from A to B will go the long way in this case here. So it's a smart algorithm in the sense it takes care of avoiding the problem of loops in a completely plug-and-play fashion, and it will react to any changes in the topology. It will repair losses. If a link breaks, it will repair it, but it's not optimal from a traffic viewpoint in particular. Here, all traffic that goes from A to B should be better going here. So some of the capacity is not used at all, and we're overloading this link probably that concentrates a large amount of traffic. That's how bridges work. So let's assume I have a network of bridges like this one. So I have 4 boxes that I call SW0 to 3 that are connected to a number of ports here. How many frames can be transmitted in parallel? So in parallel, that means if we do Wireshark or some other tools to observe and we timestamp with very accurate precision. And we say that in parallel, if the transmission is overlapping significantly, how many could be transmitted in parallel in this network, do you think? I close the poll in a few seconds. And we have a tie between B and C and D. And the correct answer is D. In fact, there can be a lot of parallelism in this network. We can have probably, depending on the assumptions we're making. But on every port here, there can be a frame in each direction. So here there can be two packets. If, for example, the switch one had a frame to deliver to A, and due to the randomness of when packets were queued, for example, there was a burst of packets coming from F to switch one that is waiting to be transmitted to A. At the same time, A transmit a packet, then those two transmissions can happen at exactly the same time. So here there can be two packets here. And in fact, the same can happen on every link here. So on every link that you see, and if I'm counting right, there are 9 links in total, there could be one frame in every direction. Of course, there will not always be one frame in every direction, but if all the switch buffers are full in a period of large traffic to be transmitted, this is what will happen. So there can be 18 transmissions in parallel. Compared to Ethernet, the standard Ethernet will allow one, right? If you cable this as a big Ethernet, there will be only one frame that can be transmitted in parallel. That's the major motivation for doing Ethernet the way it is. We use all the cables, we use massive parallelism. Of course, in practice, a lot of traffic is concentrated, so this parallelism might not be as severe as shown here, but that's the major difference. And this is why Ethernet today is based on bridges and not on shared medium. A few words about the formats. You know them already from the Lab 0, but let's have a second look at it. So this is what we see in Wireshark, the blue part except the FCS. We see a destination address, a source address, and a protocol type. There are multiple Ethernet formats, but the most widespread format is this one. The protocol type is 2 bytes, and it indicates things like, as we know, IPv4, or IPv6, or ARP. Those are the 3 protocols we have seen already. And the weird thing is that IPv4 and IPv6 are different protocol types. I mean, we could have imagined that IPv6 is IP, and there is a different version number inside the IP header. But as we have seen, this desire of the IPv6 creators was to make it a thing different than IPv4. This is why it is like this here. We've seen also that the ARP used by IPv4 is an Ethernet protocol, so this is where the protocol is used here. There is an additional field here, frame check sequence, that we'll discuss in a second, and also a preamble here. A preamble and the starting frame delimiter is a sequence of bits that you don't see, because Wireshark will not see them, the hardware discards them. In fact, they are not data bits. They are just bits that are used to allow what we can see, what we can call the asynchronous transmission of Ethernet. So except if you use very fancy things with a PTP, with White Rabbit at CERN for doing extremely high precision network protocol, except for those cases, Ethernet is asynchronous. What does it mean, asynchronous? Well, asynchrony has to do with the bit clock. If I send this packet from A to B, I send it using a signal. We've discussed that in the first week when we spoke about the propagation time and the physical layer. So we transmit bits. The bits are generated with the clock of the sender. For example, if you send 1 megabit at 1 megabit per second, it takes 1 second to send 1 million oscillations of your electromagnetic wave. Then the receiver receives those bits, but needs to sample the signal, and typically does it with its own clock. Now, the clocks are not perfect. I mean, this clock here is a cheap quartz that has an error of a relative error compared to the perfect clock of perhaps 10 to the minus 4 or 10 to the minus 5. So that's regular quartz. Extremely expensive clocks will have an accuracy of 10 to the minus 8, perhaps. But if you have a cheap clock, which you probably have on your Ethernet adapter, then it means that after 1 million bits, it may be off by 10 bits or even 100 bits. So if you're sampling the signal, and you have a very large packets, then, or after a number of packets that have been received, then there's this clock drift problem is becoming visible. Why is there such a problem? Well, because except if you build an atomic clock, the frequency of a clock that runs, for example, nominally at 1 megahertz, that means it has 1 million ticks per second. But in practice, it's impossible to make a quartz that will exactly have this. It depends on the geometry of the quartz. It also depends on things like pressure and temperature. So it varies a little, but it varies mainly by fabrication. So every clock is a bit wrong with a systematic error, which is why if you buy a watch, your watch might be is visible at the accuracy of a watch. Every watch will be off by a few seconds every day, which is very little. If you count all the number of ticks that there is in a day, the number of seconds that there is a day, it will be off by a few seconds. So you need protocols to correct this inaccuracy. This is what all our computers do. They have the network time protocol that will correct the clock of our computer every day, or even every several times per hour. This is why the clocks of our computers are very accurate. The clocks of your watch, if it's not a smartwatch or it gets the clock from a radio signal, if you do nothing, after a year, it will be completely off by several minutes. This is the story of clocks. Now, when you transmit from A to B over Ethernet, if the two links are, the two links can either be synchronized or non-synchronized. If they are synchronized, that means that we solve this problem by synchronizing the receiver clock. So we create a network that has a master clock, and we distribute with extremely expensive and very accurate timing systems. We control the clocks of all devices. This is what radio networks do, 4G, 5G. They synchronize all the base stations because they use partly some things like TDMA. I mentioned TDMA as one mechanism for multiple access. If you do TDMA, you must synchronize the clock somehow. In Ethernet, the decision was radically opposite. We don't synchronize the clocks. So instead, we have free running clock. When a sender sends, it sends with its own clock. When the receiver receives, it receives with its own clock. Yeah. And of course, what this means is that there might be you cannot send two large blocks of data once at a time. So you send one packet and then you relax a bit. So you introduce a little gap between two packets. And the gap will have the effect that if one clock is a bit faster than the other, then the gaps will compensate for this difference of working rates of the two clocks. And the packets are not too large, which makes sure that you're able to decode without having this error. In fact, you need also some assistance. You get from the signal itself some indication. If you, for example, if I send you a sine wave, you can see somehow my clock by looking at the peaks of the wave. So there are special circuits called phase lock loops that will control the receiver's clock, at least for a short duration of time. They work well, then they can accumulate error over time. And this is why packet transmission over Ethernet is asynchronous. And between packet transmission, you must relax for some time. But that means also you don't know when a packet transmission starts. So end of this long story. Because, I mean, if in a perfectly synchronous system, you know exactly when packet transmission starts. In an asynchronous system, you never know. So therefore, you try by sending 8 bytes. And whenever in this sequence of bits, you detect this pattern, you know, oh, that's the beginning of a packet here. So an Ethernet receiving system, when it sees some power on the line, it will first try to actively detect this pattern. And of course, the preamble should not show this pattern. The first time this pattern occurs, you know, is the beginning, and then you can start decoding the packet. That's the price to pay to be completely asynchronous. But this is why also Ethernet is cheap and completely widespread, because making asynchronous systems is very simple. Making synchronous system requires extremely sophisticated systems, network systems. At the end of the packet, we'll see also there's an error detection. So a frame check sequence, the frame check sequence is a more sophisticated code than is used. For example, we've seen there's a checksum in UDP and TCP header, and also in the IP header. This one is a polynomial checksum. That is something that is able to detect multiple bit errors. So it can detect frames that have an error. It can detect up to all triple errors and all bursts of errors of length less than 32 and blah, blah. So the probability that a random collection of bits error is collected is undetected is this thing here. So which means that in practice, if there is a transmission error, which is rare already on cable system, but not impossible, then it will be detected. And then what do we do in an Ethernet system? If we detect that there's an error, we drop the packet. The packet is lost. So we have our first reason for dropping packets. It's rare. It happens. The bit error, the residual bit error rate is the order of this here. And after, so that means that once in a few million packets, you might drop it due to transmission errors. It's rare if I'm doing just sending one packet, but of course, if you're doing volume transfers, this is not so rare. So once in a while, you do lose packets, and we know that we must do something about it by using TCP, for example. We've seen that the MAC layer uses MAC addresses here. Because the MAC layer is originally meant to be broadcast, this is the mental model that underlies the way addressing is done. We put a destination address, we put that on the cable. The protocol that we've seen will allow us to send after waiting some time until there's no collision, and maybe there's a collision, we'll need to resend. But once we're able to send, we put a destination address, and the system will not specifically route the packet to a certain destination. Instead, all systems will receive it. All systems are able to decode will receive it. So if it's Ethernet, it's all system. If it's Wi-Fi, it depends whether the signal is strong enough. And it will be received by whoever has the correct MAC address. We're saying that bridges are transparent, so they must simulate exactly the same behavior. By simply putting the destination address, it should reach the destination here. Now, perhaps we understand why broadcasts are so frequent in the local area network. A local area network is what IP calls a subnet, right? Because the mental model is this one: sending a packet to D or sending it to everyone has the same cost for the source, for A, that is sending the packet, and for the network. So broadcast is for free in this original shared medium Ethernet. This is why we do it a lot. And the way to send a broadcast is to simply send a MAC address, which has ones everyone, so the all ones destination address. If you put a packet with that destination address, it will go to all systems. Of course, very quickly, this became a problem. Question? Well, remember that the decoding, the system is asynchronous. So here there is nothing that is being sent. So you need the hardware first to detect that there is energy transferred on the cable. And all of this is analog, so it's not perfect. So you need to do some processing for detecting that something happens. So you may not be sure that you've got exactly the beginning of the signal here. So that's why it's for the same reason that the collision uses jam bits. We want to make sure that the analog detection is reliable. So this is why we have this which is long enough, and to make sure that everything is properly locally synchronized. So here, this preamble is used also by the phase lock loop hardware to locally synchronize the receiver clock to the signal that is transmitted here. And then this can be decoded. And after that, we will go to sleep for a few fractions of microsecond. And the next packet, we will redo the same thing. Yes, so there is no information in the preamble, exactly. This is purely physical layer bits. They are bits that are used for training the clock and starting the reception process. This is why also we don't see them in Wireshark, right? They don't exist for the software. So broadcast is for free on a shared medium Ethernet. Of course, it's not for free on the true network, but that also is consistent with why does the MAC layer do a spanning tree instead of smarter ways like routers do to avoid the looping packets. I mean, routers compute routing tables that compute paths, and we don't need to disable links. Well, one of the reasons is we want to support also the broadcast, because remember, a network of switches like this should be functionally exactly the same as that from the host viewpoint. That was the requirement. Again, if we would redo this today, probably we would find this requirement exaggerated, because now broadcasts cause a lot of problems, performance and security problems. For security, of course, if you're an attacker and you're designing malware, and if you have applications that use broadcast, then you will use the broadcast because you reach more systems by broadcast. So it's very easy for attackers. There are also performance problems. For example, if for whatever reason the software bugs here causes the software to be caught in a loop and resend the same packet again and again, if this packet is broadcast, then this will kill the network, in fact. But we want to support it. So how do bridges support it? Of course, using the spanning tree. Since we have, for example, in this case, this is the root, those ports are disabled, then it's very easy once you have built a spanning tree to send broadcasts. We don't have loop problem. The packet is sent by every bridge, and broadcast packet is sent by every bridge on all ports that are not the receiving port and are on the spanning tree. So this bridge, when it receives a packet, will forward to the host, but will not forward on this link because it's not on the spanning tree. But this bridge will forward those two links, for example. So that's very easy. Multicast came a bit after all this story. So we've seen that there are many multicast packets. For example, IPv6 uses multicast packets whenever it does any kind of configuration. So hosts and local area networks need to support multicast here. Multicast is visible in the address. So there is one of the bits in the MAC address. For whatever reason, it's bit 8, not the first bit, but the 8th bit. So which means the last bit of the second hexadecimal digit. When it's 1, it means it's a multicast address. So those are multicast addresses. The most frequent addresses that we will see are for IPv4 multicast and for IPv6 multicast. For some reasons, as you can see, IPv6 uses a different space, which is again consistent with this philosophy that IPv6 is not just a new version of IPv4, but it's protocol of its own. Then in the industrial world, in particular, the MAC layer is used a lot in industrial networking. For example, in factory automation, many networks are just one big local area network. In substation automation, in electrical grids, for example, the software that runs and all the communicating devices that run in a substation use also just MAC layer communication. Then there are also, for example, this is the timing protocol that's used for phasor measurement units. If it's a non-IP protocol, it can use its own, whether it's an IP or non-IP protocol, it will tend to use its own MAC addresses here. Here, that means all the devices that are switches that want to be synchronized by this protocol. We will talk about multicast a bit later in the multicast lecture. Functionally, if the network is truly shared medium, then multicast simply means that the hardware will filter out all the packets that are not required by this host, because the host doesn't subscribe to multicast. For example, if it's one of the IPv6 multicast that we've explained before. Yes, if let me skip. No, not skipping. When we have bridges, then we will see how bridges take care of multicast here. There is no multicast protocol at the MAC layer. So in principle, the only thing that can do a bridge, that the one you buy at Migros, it will handle all those MAC addresses that are destination that have 1 in the 8th bit. It will handle it at broadcast. Will send them over the spanning tree to all bridges, therefore de facto making it a broadcast. We will come back to this multicast handling a bit later when we talk of IP multicast. Right now, a few questions. Let's start with this one. I close the poll in a second. And of course, the answer is B, which is also the majority vote. The protocol type in an Ethernet frame indicates the higher layer, which is perhaps IPv4, perhaps something else, but TCP typically would be an even higher layer containing IPv4 packets. So you don't know by looking at the Ethernet frame whether it's a TCP packet or not. Worse, you don't know the port number. So bridges don't know the port numbers, for example. Now let's go back to our network where we've replaced every physical cabling by switches, and assume we were working with IPv4. Then one day comes IPv6 in, of course, the software in all the hosts need to support IPv6, which is not a problem if you have recent versions of the operating system, which you should have because otherwise you're vulnerable to security problems. But do we need to change the bridges? So when EPFL introduced IPv6 a few years ago, or at home, if you have bought your little box to extend your Ethernet cable to another room, and then all of a sudden Swisscom now says to you, now you're working in IPv6, or you buy a new printer, and now the new printers you buy by default, they're plug and play, they have IPv6 addresses, but you also have an old printer that has IPv4 only. Do you need to do something to your bridge? I close the poll. And the majority says A, which is the correct answer. In fact, if you buy those Ethernet concentrators, it will not say IPv6 compliant or works with IPv6. They might add a sticker works with IPv6, of course, but it works with anything because it doesn't look at the IP header. With a small catch, we will see a bit later that you can have smart bridges that try to do something about multicast to avoid broadcasting the multicasts. Now, such bridges are cheating. They look at the IP headers. So, of course, then those will not do the optimization if they're only for IPv4. But they will still work with IPv6. They will not optimize the IPv6 multicast. They will treat them at broadcast, but they still will work. In fact, that's one of the major reasons today why we still have the MAC layer, is that we have IPv4 and IPv6 that are two protocols. The MAC layer was very useful 20 years ago because we had AppleTalk, Novel Netware, IBM SNA, Microsoft, blah, blah, NetBIOS, etc. All non-IP protocols that were running together. And the MAC, we could interconnect them if one day you decide to install novel NetWare instead of Microsoft NetBIOS on your PC, you didn't need to change the switches. So that was the reason 20 years ago for having MAC layers, or the reason why MAC layers survived and was not replaced by everything done at the IP layer when IP swept out all other protocols. But then there were IPv4 that swept out all other protocols. But then there's IPv6 that comes. So the world today is in reality by protocol. We have IPv4 and IPv6. Those are two protocols, there are two networks that in fact are different. So it's very convenient to have, at least at the lowest layer of the internetworking, to have something that doesn't care about those differences. And this is why we are still happy to have the MAC layer. Perhaps in 50 years, in 100 years, in 2,000 years, if the Earth survives the climate change and the atomic war, we will have only IPv6, and then we will not need the MAC layer. That would be beautiful. When we work with local area networks in places like EPFL, in fact, we're immediately confronted with what is called virtual LANs, which is really the extreme of the logic. Virtual LANs exist only because we have the MAC layer, and the way it is, it doesn't solve all the problems that we have. Therefore, we create virtual LANs. When the MAC layer will disappear, the virtual LANs will disappear. Why do we have virtual LANs? Well, here is an organization that has three types of machines, and we have that at TPFL. At TPFL, we have our hosts that are on the Wi-Fi network. They have a certain of access rights. Then you have other machines, for example, in the payroll department, there's a number of machines that do a number of things. And you may have separation of those networks. So the state of the art today to separate the networks is to write filtering rules in the routers, plus additional security mechanisms. But a cheap mechanism is to put on the same local area network all the things that go together here. So some systems use local area network as access control. For example, it might be possible that if A and Y are not in the same local area network, which is, for example, the local area network of the human resources department, where all the people are sitting in the same floor, they're all cabled together, and if you do not have a machine that's physically connected to one of the Ethernet sockets of that floor, you don't have access to the computer. So many companies do that. That is a primitive but efficient way of providing some security perimeter. You know that an attacker must first physically gain access to your location and use one of the physically connected systems. So that's the first motivation for virtual LANs. Of course, then if you do this, you put also a lot of constraints. That means all your employees of the human resource department, they have to be on the same floor. Right? Now, the reality of floors is that in companies and administrations, every 5 years, they're completely reorganized. So we decide that all employees of the human resource department are in the same corridor. Then comes a new head of the company or a VP of EPFL that decides, no, now each of them will sit in the different labs or schools where they work. So they're all of a sudden, they're no longer in the same department. But we were using their physical connectivity to give them access to sensitive application. Solution is virtual LAN, is to virtualize the physical connectivity. So now you may decide that G, C, and D, they should be treated as being in the same local area network here. So decoupling physical location from local area network is what is done by virtual LAN. If you think about it, that's a bit crazy because the LAN is providing physical connectivity. So if you're physically connected together, then you're connected by the same switch. Now, if you're not, why do you want to do as if you would be in the same physical connection? Well, it's because there is some software that looks at this. How can the software know you're in the physical, the same LAN or not? How can I have an application that accepts packets that only come from someone who is in the same local area network? Well, there's millions of ways. We could look at the source IP address. and make sure the IP address is in the same subnet as me. Or I can force the client application to send packet with TTL equal 1. Then I'm sure this will never go anywhere else, at least on the client side. So I can do a number of steps to check this. Now, but because such applications exist and we want to support them, there are also applications like AirPlay or iTunes. They work also in the same LAN. They don't go through routers. So if you want this to continue to work. Another application is, in fact, at EPFL, when we connect to the Wi-Fi network of EPFL, the first thing we do in the morning when we arrive is an association with a base station. And depending where we associate to which base station, there's above 1,000 base stations at EPFL, we are allocated one to one local area network or another. The EPFL Wi-Fi network is not one huge local area network with bridging between all. That would not be efficient because we know bridges are not efficient. They can support only small number of destinations because they do exact match. So for every packet, you need to screen exactly. So we want still to have limits on the size of a local area network. What is done at EPFL is it uses virtual local area network. In the morning when you arrive, you join in this room, you belong to the local area network of this part of the campus. When you move in the rest of the day, you will continue to be part of this local area network virtually using the virtual LAN technology. How does it work? Well, that's very simple. We use what is called a VLAN tag. So in the Ethernet header, it's supported by the Ethernet header. If instead of using the type number here, we put a VLAN tag, so if we put a number here, of course, we must make sure that the first 2 bytes of the VLAN tag never overlap with any valid type, which is sure because the first 2 bytes are those 8100. So if the first, in some sense, if the type is this, that means it's a VLAN ID, and then we have 2 bytes to say what is the ID that the LAN that you belong to. This is done by the switches on their ports. So of course, those are not the switches that you buy at Migros that do this. Those buys do not do that. You need to manage the switches to do that. You must set up rules to decide which VLAN is authorized and which. Otherwise, of course, that defeats the purpose. If anybody can pretend they are in the human resource department VLAN, then there are rules like DHCP server that you need to configure somehow those switches. When you're a host, you don't see this. If you do Wireshark at your host part, you will not see the VLAN tag because that, again, this has to be transparent to the host. But when C is sending a packet to S1 here, then S1 configures the port. So this is where the management part comes. This port is configured as belonging to the red VLAN. And then all the switches here, they maintain one spanning tree per VLAN. So they have a red spanning tree, a green spanning tree, and a blue spanning tree. And they have a red forwarding table, a blue forwarding table, and a green forwarding table. Of course, they don't have physically n different tables. They have a big table with a VLAN ID. And when you search the table, you first get an index to the VLAN ID, and then you search for the destination that corresponds to this. So we have, as if they had separated virtual local area networks. And when S1, for example, receives a packet from C, and if it's the first time it sees the packet to be sent to G, it will broadcast it over the red spanning tree. The red spanning tree will be broadcast over all the trees here. So even a switch like this one that has no red host will still need to run the red spanning tree. So the spanning tree will be S1, S2, S3. The packet will go to G. And then all the bridges on the path will learn in their red routing forwarding table where the source address of C is. They will learn in this direction. So they will learn the MAC addresses like they do otherwise, but they will put them in the corresponding red, blue, green tables here. So now, of course, there is a small problem here. When S1 sends a packet to S2, it must know whether it's a red packet or a green packet. This is what the VLAN tag will say. So this VLAN tag is put only by bridges on the links between bridges. Sometimes those links are called trunks as opposed to ports here. So a bridge must know whether it's talking to a bridge here or to a host. And this, of course, is done by network configuration. And when it has a red packet to send, then it knows it's a red packet. So when S2 receives a packet from S1, it looks at the VLAN tag, knows whether it's red or blue, and goes correspondingly to the forwarding table and sends it also on the corresponding spanning tree if it must be broadcast. This is how VLANs work. Now a little quiz. Mm-hmm. I close in a few seconds. And we see a tie with a short majority for B, but it's not correct. The correct answer is C, which is because if, so we said A has a packet to send to C, right? Now, they're not in the same virtual local area network. They're not in the same VLAN, but a VLAN is like a LAN from, in fact, from A, there's no difference whether, so for A, it is as if A and Y will be sitting on a physical concentrator or had an Ethernet cable here, and C and D are also on another one. But of course, the goal of VLANs is to separate. So when A will analyze the destination address, of course, the subnet prefix and mask applied to C will give something different than the subnet prefix of A. So there must be in different subnets, which must be reflected in the IP addresses here, which means that A will not send directly to C. We'll see that A can send directly to Y by getting the MAC address of Y, so by sending an R packet that will be broadcast into the green VLAN. But when A sends to C, it doesn't work at the MAC layer because they're not in the same local area network. So we need a router. We need a router, that's the principle of the internet, to interconnect LANs, and also to interconnect VLANs, we need routers. In the most primitive way, that means we need a router that is connected to both the green and the red VLAN. That means we need to configure this router here to accept the packets that are green and red, and also S1 to decide that this port that goes to the router is part of the green and red VLAN. In practice, this is not the way it's done. In practice, the same physical box contains the router and S1 most of the time. So they are in the same box, but the router function is different codes. In S1, you have the bridging function that looks up the runs the spanning tree protocol, does exact match in the MAC address forwarding table. Then there is other lines of code that are looking at the IP routing table and is configured in a different way. So functionally, it is the same as if they would be separated. And then the packet must go through a routing function to be able to work here. A few more words on special technologies. We've seen that bridges, of course, can be used to extend the local area network of Ethernet. For example, an Ethernet concentrator, that's the box you can buy from Equal. It's a bridge today. 20 years ago, it was physical layer wiring. It was just connecting the wires, and then you had the CSMA CD protocol running everywhere here. But we can put a bridge. I've said in the first week that we put a router to interconnect different LANs. But as everything I'm saying, it's only a first approximation. The reality is a bit more complex. We can put a bridge if we want. We can bridge between Wi-Fi and Ethernet. And in fact, if the only limit for doing that is the size of your network. At EPFL, we don't do this because the Wi-Fi network is already too large, but we can do it at home. You probably can do it. What's the benefit of doing this? Well, simplicity. I mean, if I put a router here, if you put a router at home, you have to do a numbering plan. You have to decide my first floor or my garage where I have all my servers is this subnet, and this is another subnet, and you have to put the bits right and the masks and so on. If anything is wrong, it will not work. Your network will not work. So it comes with configuration overhead. A bridge will not. You just connect and it works here. This is typically used in Wi-Fi distribution system. So this is the typical use, for example, at EPFL or practically everywhere. Not everywhere, there are a few suboptimal things, but when you have Wi-Fi somewhere, then all the Wi-Fi base stations are connected together via Ethernet. You don't connect them via Wi-Fi, because if you would do this, it's possible to do it, but that you have a problem with the collisions and the repeated collisions. Right? Wi-Fi allows one frame at a time. Here, if we connect them via Ethernet, then we allow one frame per Wi-Fi that is not physically interfering. And if you want to keep it simple, if the network is not too large, then you typically do it via bridging over Ethernet here. So you can build one bridge network as long as you don't have more than a few hundreds of hosts running on Wi-Fi. That will work and is the simplest way. Even in this case already, the Wi-Fi frame has a small problem here. For example, when we say when A sends a packet to G, so G is one of the servers, for example, your DHCP server that is connected to Ethernet here, then we said the principle is I create a MAC at the MAC layer, source A, destination G, which is what we do, source A, destination G. But if we go via a base station here, in addition, the MAC protocol requires, in fact, to have a Wi-Fi end system. So to detect the collision, to do things like the RTS, CTS, we need the MAC address of someone who is the base station here. So if you do a Wi-Fi Wireshark of a Wi-Fi packet, you will see things like the source address, the destination address, and the access point address, which you will learn at the time you configure, you connect here. So this is why in Wi-Fi packets, we can see 4 MAC addresses. I will conclude with this last exotic things that sometimes exist. Now, if instead of doing the state-of-the-art thing, which consists in interconnecting all your base stations with Ethernet cable, if you don't want to do this, for example, because it's too expensive to have Ethernet cable, you can connect them via Wi-Fi. From a performance viewpoint, it might not be very good, but functionally it works. In such a case, you might have something like when A talks to B, then we'll go first to the base station, that goes to another base station, that goes to yet another base station, etc. This is all one MAC layer, one subnet from the IP viewpoint. It's all one local area. Then we have a problem for the packet, for the Wi-Fi frame, as it goes from M2 to M3. The Wi-Fi protocol requires a source and destination address that are local to the Wi-Fi protocol when M2 is trying to send to M3. So we need to have the address of M2, the address of M3, the address of A, and the address of B. This is why, if you do, in such a case, a Wi-Fi analysis with Wireshark of your Wi-Fi packet, you will find source address A, destination address B, and then fields like transmit access point address and receive access point addresses. So you can find up to 4 MAC addresses. Other than that, the Wi-Fi header is essentially like the Ethernet header. Voila, thank you for your attention.